Let's get some procedural stuff out of the way. So first of all, is I'm expecting a technician from the gas company to come to my apartment sometime, and I have a maintenance request because I have water leaking into my apartment. So like, there's a good chance that this lecture is going to get interrupted with, my real life stuff. So I apologize in advance. And if that happens, there'll be a cutaway and there'll be editing and such to make that more seamless. Let's see, past assignments. Homework 1 solution should hopefully be posted today. Homework 2 is due today. People wondering, like, what are the correct answers in the quiz? Like, I thought the quiz should tell you immediately whether or not you got the right or wrong answers. If it doesn't, I'll have Kushagra cook up something that puts the quiz solutions. Quiz 2 still not graded. Yeah, quiz 2 still not graded for anyone, I think, which is really confusing to me. Maybe we had a Brightspace hiccup. It gives you the score, but it doesn't give you the answers. Yeah, I will look into that along the other side things I'm going. Exam is the big thing coming up this week. People asking, oh, how is it going to work with Brightspace and Respondus? And I'm like, the short answer is we're actually still figuring this out. We're having some problems where Respondus is being overzealous and it's preventing access to too many services. Like it's not allowing you to even print the exam or stuff like that. So we're trying to work out all the bugs. Boyu and I are. So if for some reason, like we don't get things worked out by Friday, we just won't use the Respondus system. It'll be administered just like a quiz. But fingers crossed, we will have everything worked out by then. The idea is we'll have some sort of survey up where you can test out the system before the exam goes live. Brandon's question, are there any other practice exams or problems other than the ones on Brightspace? I don't plan on providing any more. Now, I'm sure if you were to ask someone who took the class in fall of 2021 or maybe spring of 2021 or any time during 2020, you might get some more answers and more solutions, but I don't plan on posting any more. If you think that, the 2 exams you provided are inadequate, do let me know. Exam 1 material covers lecture set 1 and lecture set 2, and only lecture set 1 and lecture set 2. So from the beginning of the course with syllabus stuff and the ideal op-amp all the way up to switch circuits with ODE methods. I will, this week, I will teach lecture set 3 on convolution. However, if you have any questions about how to do an exam problem or work through this exam or give me a brief lecture on, a certain topic from the start, we'll do that. Ideally, if you want me to work out a problem, let me know in advance so that I can have something nice prepared rather than holding up paper to the camera. With that being said, I think that covers the procedural things. We have hit our threshold voltage for today, 30 students. Is there anything someone wants me to discuss in lecture right now? Solutions for homework 1, hopefully posted today. Going once, going twice for things you want discussed about the exam. I assume no questions means everyone's like, give me the exam tomorrow. I'll get 100%. No, I'm kidding. You're not guaranteed to receive the same grade if you work in the group for homework. The idea is, you're graded based off of the work you show. That's the answer. So if you just copy down answers, you will not get a good grade. The exams are freak, as in the frequency domain, or free response questions. Yes, the exam's all free response questions. Yes, the exam will look very similar to a quiz. We're working out how to use Respondus so that it ties in there. We will give you directions hopefully by Wednesday, so that you can work out the system and see what it looks like yourself. But it's going to look very, very, very similar to a quiz in terms of how you take it. Mahir, what does NP per S mean? That's units of Nepers per second. So if you look up Neper unit in Wikipedia, it'll tell you that Neper is basically the argument of an exponential function or a hyperbolic function. It's basically a measure of attenuation. Oh, yes, Barat, time-wise, yes. It's going to be in the same time window of noon Friday EDT to 11:59 p.m. Saturday EDT. Brandon, the answer is free response questions. Yes, upload to Brightspace somehow. We're still working out the logistics of that. We ran into an issue where, we were testing the system. We had it working slightly, and then it just stopped working. So we were trying to figure out what's happening. Exams graded like the homework. Yeah. Like I create a solution key where it's all additive. You get 1 point if you have the right KVL equation, maybe, for instance. You get 1 point for having the right, intermediate voltage calculation, and then, 1 point for the final current answer, however it is. Nepers per second is a unit. Yes, it is. I'm trying to get people used to using proper units for things. And again, Neper is a very weird unit. Like radians, it doesn't really exist. It disappears when it's not needed. Any more questions? Yeah. Was there a possibility to re-upload Friday's lecture? I'll try. I'll see if I can get it to work. Sorry, I didn't realize people were having issues viewing it. Yeah, those are the kinds of things where, hey, just let me know. I don't sit through and listen to myself. It's really hard to listen to myself on a video. Just my voice sounds so weird to me. I think that's true of a lot of people. Nice voice. I'm glad you think so, but Okay. So should be sharing my screen now, and I was going to show you, here's the Wikipedia page for Neper. It's the logarithmic unit for ratios of physical field and power quantities. Comes from the name John Napier. It's not part of SI, but it's acceptable. And as you can see, it works very well with the natural log. So these are it is the sort of, fancy way of having the units be correct. So I just want you to be exposed to this so that it doesn't confuse you later on in your life. Okay, let's go lecture set 3. So we said we would cover discrete convolution, which we did on Friday. Sorry if you couldn't view that video. I'm working on that. Algebraic convolution is the topic for today, where we're going to talk about the continuous time convolution. So we're going to do some review after function transformations after we define some simple causal functions. We'll define convolution and then do some properties and some examples. And then we'll lead into graphical convolution. And then we'll talk about the impulse response and then numerical impulse response. So using numerical techniques. So convolution, I call it the fundamental operation of electrical engineering. Contrast that to addition, subtraction for accounting, and exponentiation for finance and macroeconomics. So what have you. And we talked about discrete convolution, not because it's something that's really tied into circuits themselves, but it's a good warm up for what we have. So we said Kronecker delta function is the identity function for convolution. The Kronecker delta function is named after Leopold Kronecker, a German mathematician. He has a few things named after him in like set theory and things like that. So, we're saying if you convolve a signal with the Kronecker delta function, you just get the same signal back. It's the same as, multiplying by 1 or adding 0. If you convolve with the Kronecker delta, you get the same function back in continuous time. We also have this unit step function, which is the indicator, which tells us when a signal turns on. We came up with our discrete time convolution definition. And then we worked through like, okay, we have functions f of n and g of n. We put them both on the m track and let them collide, where we reflect g of n into g of minus m. Then we add, n for the position that the train is chugging along the track. At -1, there's no overlap, so our running convolution is 0 up until that point in time. At time equals 0, there starts to be some overlap, so we finally get a convolution answer at a time instant when we sum over all of time after multiplying. And then we kept building up more as the functions, collided more and more. Eventually, they reached a point where there was a maximum collision and they stopped overlapping as much. And the convolution sort of trailed off until we reached our last point at n equals 7. And you can do the same thing tabularly because, you can write everything as sort of like a, shifted bit of impulses. So you can basically get these sort of scaled versions of f of n, time shifted a little bit, and then you just add them up over time and you get this, where the scaling comes from g of n. So, definitely ponder about this. There is a small error in the textbook for the n equals 3 answer, but I'll speak to Art about that, get that corrected for future versions. But yeah, if you're confused about this, the textbook, is going to have a lot more pictures and stuff like that that really help you understand convolution. Homework 3 is going to have a YouTube video that explains continuous time convolution a little bit better too. So. Convolution does take a little bit to wrap your head around, but we think you can get it with enough practice. Will you have any questions like problem 5, homework 2 on the exam? Keaton, what was homework 5, problem 2 on homework 2? I don't remember. Just a differential equation? I would say there's a good chance. You will see, just a plain differential equation without a circuit context. As I explained to someone, what's the odds of seeing a switch circuit on the exam? What's the probability of seeing a switch circuit on the exam? In the, intervals 0 to 1, I'd say closer to 1 than to 0. ECE 302 jokes. Okay. So now let's go back to discussing convolution. Now we're going to talk about algebraic convolution. So first of all, we're going to talk about the move from discrete time to continuous time. So for the remainder of the course, we're going to work with continuous time convolution and not touch discrete time convolution ever again. And we're going to expand the theory of continuous time convolution in order to solve circuit problems. So conceptually, the continuous time version of convolution is very similar to the discrete version. The challenge is, as you work with smaller and smaller intervals, you could take a limit, and eventually you'll see that you're multiplying continuous time functions rather than just multiplying functions at discrete instances of time. That's going to be annoying but doable. And then we're going to do an integral instead of summation. And oh boy, integrals are a lot harder to take than summations. So before we look at the convolution integral, we're going to introduce some helpful functions and review some function transformations. So here we go. So this is the unit impulse function. denoted with a lowercase delta, and of its function of variable. So formally, the unit impulse function, also known as the Dirac delta function, is defined as a function such that the integral is the unit step function. We haven't talked about the unit step function yet, but this is the definition. So the integral from tau equals negative infinity to t of delta of tau d tau is equal to u of t. Well, that's not very helpful yet because we have to define it in terms of something we haven't explored yet, but we'll work around it. So first of all, Paul Dirac was an English theoretical physicist who helped develop quantum mechanics and quantum electromechanics or quantum electromagnetics. So, he was a very interesting person. He was known for being weird even among physicists. So, he was hard to relate to as a person. So, first of all, we called this the Dirac delta function. And if you're a mathematical purist, you would argue that the Dirac delta is a distribution, not a true function. It doesn't meet certain criteria for what a function should be. But regardless of what you call it, there's no hindrance to using it as an engineer. We're going to use it as though it were any other function. So one way to look at the unit impulse function is as a limit of shorter and shorter pulses with unit area. So the end of the limiting sequence would be the confounding definition below. So if you looked at, the true limit, we would say delta of t is 0 everywhere that t is not equal to 0. And at time equals infinity, it is this infinitesimally thin spike up to infinity. And something that's 0 and then infinity, but, over an infinitely thin area, that doesn't make a lot of sense. So that's very hard to work with. And understanding the peculiarities of the, unit impulse function is definitely something that, takes a little time. You got to really sort of ponder this and figure out, okay, how can we have a function that's this poorly behaved and get useful answers out of it? So the key is you do not want to use the value of the unit impulse function at the moment all the action happens. For us, that would be t equals 0. You don't want to just say, okay, here's a delta function. What's 1 plus the delta function? You get something that's like 1 everywhere, and then 1 plus infinity, or just infinity at time equals 0. That doesn't work out very well. The unit impulse function doesn't like to be outside of the integrand of an integral. It really likes to be inside of an integral. So, and having unit area under it helps, give some nice properties. So let's look at one limiting sequence for the unit impulse function. So I said, one way is the limit of shorter and shorter pulses with unit area. So here's a bunch of rectangular pulses with unit area. This is easiest to use for computation. This is how it was taught to me in my ECE courses. And, I think I should do the same and do that. So we'll define a function rect with a subscript w of t, where w is a parameter. This function is 0 everywhere that the absolute value of t is greater than w over 2. And then between minus w over 2 and positive w over 2, it takes a value of 1 over w. So here's the blue function, rect 1 of t, where we can see its width is 1 and the height is 1. So it's a little hard to tell at the scale, but yeah, this is a unit area right here. And then we have rect 0.5 of t, where it goes from negative 0.25 to positive 0.25. So width of 0.5 and a height of 2, which is 1 over 0.5. And then the brown function, it gets skinnier and taller. And then finally, this black function is the skinniest and tallest of them all. And then we could keep going until eventually you can see that the width would get smaller and smaller. It would just be width only consisting of the positive y-axis. And then the value would be infinite there. And then 0 everywhere else. So if you can't wrap your head around what the delta function itself looks like, which, that's partially the path to madness, then, you think about, okay, we're continuously deforming all of these rectangles such that the width becomes 0, but the height becomes, 1 over that small number. However, there's another way to look at this. I would also look at it as a limit of Gaussian functions. You might ask why, the previous one worked well. It's good for calculations. When I actually took a class in modern physics and quantum mechanics, this definition was a lot more helpful to me because the Gaussian function is nice and smooth everywhere. So that means all its derivatives and integrals are well defined. And, when you do analysis, you really want to have a function that has nicer properties than these, discontinuous functions like this. So even though it's not zero for all of time, in fact, it just asymptotically approaches zero, going to minus infinity and positive infinity, we'll use the normal distribution with mean mu equals 0 and a decreasing standard deviation. So if you were to crack open a probability textbook or take ECE 302, you would see that Gauss sub sigma of t, maybe mu sub mu comma sigma, but mu is just equal to 0. We'll say it's 1 over sigma times the square root of 2 pi, all times e to the negative quantity t minus mu closed quantity squared over 2 sigma squared. Plot these out, and you can see Gauss 1 of t is very, very broad. It looks almost like, it continues for a very long time. The red function, which is like the square root of 1/5, gets a little taller and then starts to go down a little faster. The brown function is, standard deviation of 1/5. And as you can see, it starts to look more like a Gaussian function where, it asymptotically approaches 0, has a bump, and then asymptotically approaches 0 again. The black one, which is the square root of 1/25. No, that's not right. It's, I guess it's the cube root of this, or the cube of the square root of 5 reciprocated. Anyway, 0.0894. It gets taller and skinnier. And then finally, the light green function is the skinniest and tallest of them all. Let's see, what questions do we have? ECE is the path to madness. Certainly with some of these functions, the delta function particularly is madness. Seeing no questions, we move on. So we'll talk about the unit step function now. So the unit step function is defined above. So u of t is equal to 0 for all time less than 0, and is equal to 1 for all time greater than or equal to 0. Now, as long as the value at t is exactly equal to 0, is somewhere between 0 and 1 inclusive, things are fine. Some define it to be exactly a half in between. It doesn't really matter for most applications. But this is the definition we'll go with for this class. So we'll say at time equals 0, it is 1, and then for all time greater than 0, it stays at 1. This is called the Heaviside step function, if you don't want to call it the unit step function. That's what things like Wolfram Alpha define it as Heaviside. And Oliver Heaviside is a very interesting person. So he was an English mathematician physicist who was the first person to apply complex numbers to circuits. He developed vector calculus. He created the Heaviside cover-up method for partial fraction expansions. He was the one who actually simplified Maxwell's equations from 20 equations in 20 variables to 4 equations in 4 variables. So he did most of the work, but Maxwell got most of the credit. Developed the transmission line theory, and he named several doubly terms. If the term ends in ants other than resistance, so like he named like capacitance, inductance, permeance, permittance, susceptance, admittance, impedance, all those things. So Oliver Heaviside did a lot. Worth reading a biography on him if you have some time. So the derivative of the unit step function is the unit impulse function. So the derivative with respect to time of u of t is delta of t. Before we were saying you could treat it as though it were 0, but that doesn't exactly account for what happens exactly at t equals 0 where there's a discontinuity. So because of the discontinuity, you basically get a delta function where, it's almost infinite slope at that point in time. That's one interpretation of what this means, is that it's constant for all time, except at t equals 0, where there's a discontinuity. And in order to account for that discontinuity, you need something with unit area, which is that delta function. So whenever you multiply by the unit step function, it causes the other function to appear only when t is greater than 0 and be 0 for all time before that. So it's an indicator function that tells us the signal is causal. Causal basically means you can say that the signal only turns on after a certain point in time. So if you take, sine of t times u of t, you get a sinusoid, or you get something that's 0 for all of time, and then it behaves like a sinusoid for all time greater than that. You can offset the unit step in time to delay the appearance of the function being multiplied. So here we'll define function a of t, which is u of t minus t naught. So this is 0 for all time less than t naught, and then after a time t naught, or we'll usually have t naught greater than 0. So it's going to be 0 at time equals 0, it's still 0, and then at t naught it jumps up to 1 and stays at 1 for all time. So one thing it's useful to do is look at our limiting sequences for the unit steps. So I'm just going to take 2 of them rather than show the whole family. You can kind of hopefully figure out. The unit step functions exist nicely as is. There's benefits to looking at in terms of the limiting functions for the direct delta function. So if we see rect I sub w of t, it's 0, and then it's this, line segment in red, and then it's red. So between w over 2 and positive w over 2, it's nice and continuous between values 0 and 1, which we're approximating as this blue function. As we make w smaller and smaller, this slope gets larger and larger, and the time where it actually jumps up is smaller and smaller. And then, so we have a nice continuous function when we look at our rectangular approximation to the delta function. And then Gauss I sub sigma of t is smooth but transcendental. Again, we'll have mu equals 0, but it's 1/2 1 plus the error function of t minus mu over sigma times square root of 2, where ERF represents the error function. People who have dealt with things of the form e to the negative variable squared know that you cannot take an analytical integral of that. You need a special function to handle that for you. So we need this transcendental function called the error function in order to represent it. And as you can see, it's in brown. And, it starts at 0 or asymptotically approaches 0. It kind of curves up, reaches a value of 1/2, and then curves back over like that. So yeah, it's still a smooth function, which is very nice. And as you can see, as you make sigma smaller and smaller, it'll curve in less and less time, so that eventually it stays 0 longer, has a steeper slope, and then it stays close to the value of 1. On slide 20, we will say how you make a rectangular pulse from unit steps. So we'll define C of t as u of t minus t1, and then t minus u of t minus t2, where we're assuming t2 is bigger than t1. Should probably write that down. So we assume t2 bigger than t1. So that means we'll have a function that is 0 for all of time up to t1, and then also 0 from all the time greater than t2, because of the subtraction of 2 things that take a value of 1. And then in between, it takes on a value of 1 between t1 and t2. So by subtracting 2 net steps with different time shifts, we create an indicator that lasts for a finite duration instead of being half infinite. So multiplying by a rectangular pulse returns the other function only over that time interval, t1 to t2. So this can save a lot of confusion when working with simple signals. We can only think about, okay, in this segment of time, we have this function existing, and we don't care about what happens outside of that segment of time because we don't have to worry about it. We can just write another rectangular pulse times a function to describe its behavior. This will come into play when we talk about graphical convolution a little bit. It's going to save us a little bit of brain power. So I encourage you to think about things in terms of this, rectangular pulse. Because it's easier to think of the pieces of function existing independently over an interval than as an accumulation of all the operations up to a given point in time. What questions do we have? Madness and sadness. Any questions? Hearing none, we'll continue with the final of the three simple functions we're introducing. And by simple, I don't mean that they're like easy or anything like that. I mean that they are, a nice basis of functions that, define, certain polynomial techniques. They are the basis of causal signals because we're dealing with signals that are basically 0 before time equals 0, and then they turn on, and then they behave like polynomials. So we defined something that behaves like point-like, something that behaves constant-like. Now we need something that behaves linear-like. So this is the unit ramp function. It's defined as t times the unit step function. So if you take its derivative, it's the unit step function. So you'll get 1 times u of t plus, by the product rule, t times delta of t. But at any time that the delta is non-zero, the other function is 0. So you might have 0 times infinity, but we're just brushing that under the rug with a broom, and we'll just say that the derivative of the ramp is just the unit step. Mathematicians are really going to dislike how I prove this, but we're engineers. Sometimes we have to break with formality in order to get anything useful done. Now, if you do that on your homework and you're not allowed to, that's another story. But there are times when it's okay to break with formality and assume that it's okay to do this. The unit ramp function is mostly there to tidy up the statement and solution of some problems. So it's easier sometimes to write, triangular waves or sawtooth waves with the unit ramp function. We can generalize the integrals, which are no problem, and the derivatives, which is an increasing amount of issues, to the unit step function to create the basis of causal signals. So one can imagine we define a signal whose derivative is the ramp function, which looks like, 1/2 t squared u to the u of t, and so on and so forth. We could just keep taking integrals of this function and there'd be no issue. Derivatives are a little bit more complicated because you will eventually run into insanity when you start taking the derivative of the unit impulse function. And it'll hurt your brain to think about, especially if you use the rectangular definition. The Gaussian definition allows you to take derivatives of the unit impulse and at least get something that's sensible for your limiting series. So this is madness. So how does the ramp behave with our limiting sequences? So in blue, we have the ramp where it's 0 for all of time, and then it behaves as, f of t equals to t for all t greater than 0. So with our rect I squared of sub w of t, it's 0 and then it's t, outside of w over 2. But inside this, interval of width w, it basically behaves like this shifted parabola, where once the parabola matches unit slope, it just behaves like, t for all time greater than that. So not only is, this function continuous, it's also differentiable everywhere. So that's even nicer. And taking the integral of, a constant in the error function gives you this, Gauss I squared sub sigma of t, which it's complicated, but I present it here for your viewing pleasure. And you get this Brown function right here, where it's not, quite as good, asymptotically approaches 0, and then asymptotically approaches t. But as you can see, it's just, there's just this little curve rather than being a sharp angle at time t equals 0. Those are our simple causal functions we have introduced. What questions do we have? Hearing no questions, we'll move on. So let's review some function transformations. This comes from, sort of algebra and pre-calculus type of class. So if we have a base function f of t, what happens is we apply the 4 different, linear transformations on it. So if we have f of, quantity t plus, or f of t plus b, it'll shift the parent function b units to the left. Remember, even though it's plus b in the argument, it shifts it to the left. I guess by your perspective, this is to the left. From my perspective, it's the other way around. If we have f of t minus b, it'll shift the parent function b units to the right. F of a of t compresses the unit function horizontally by a factor of a. F of negative t will reflect the parent function about the y-axis. And then negative f of t reflects the parent function about the x-axis. C times f of t will stretch the parent function vertically by a factor of c. F of t plus d will shift the parent function d units up. F of t minus d, d units down. And then we've assigned a priority to the transformations to say, okay, you should take, this transformation first, then that one, these two second, these two third, these two fourth. That's the order you should do all these transformations so that you can, compose these transformations one after another. And I will say weird things happen with some of our causal functions. So the delta function has this weird property that delta of a of t is 1 over absolute value of a times delta of t. So avoid using the second priority transformations on it because they just don't make a lot of sense. You've really got to stretch your head to understand why that one is true. So I'll just avoid it whenever possible. However, some people, myself included, like a different view of function transformations. I take a transformation that goes like this. So I first of all say, factor, everything out of that. So we're left with, argument t by itself, plus or minus something in parentheses. So that, it still shifts the parent function b units to the left if it's a plus b, or b units right if it's a minus b. But then if we have a times f of a times quantity t minus b closed quantity, it's going to compress the parent function horizontally by a factor of a about the line x equals b. So before it was doing it about the y-axis, now it's doing it about a line x equals b. And then if we have f of minus quantity t minus b closed quantity, it's going to reflect the parent function about across the line x equals b. And then we can shift the up and down first by d units. And then if we factor out the negative sign, it's going to reflect the parent function across the line y equals d. So instead of about the x-axis. And then if we have a c, it's going to stretch the parent function vertically by a factor of c about the line y equals d, if we factor it like this. Note, nothing changes to the unit step function when applying the factor a in this view, because if you're always stretching it horizontally about its discontinuity where all the action happens, then it's just constant functions that continue for all of time. So when you stretch and squeeze them, it doesn't do much. It doesn't do anything. So here's a little example of successive function transformation. So in light gray here, we have the function hyperbolic sine of t. And if you're not familiar with what that function is like, well, you can always plot it out for yourself. But for now, it's just our parent function. If we take hyperbolic sine of t minus 0.5, then what that's going to do is shift our parent function 0.5 units to the right. And someone is at my door, so feel free to talk. It's probably maintenance. Let me stop class real fast. I'll leave the call going in case I get done. We talked about how we got this blue dashed line. So now if we apply a factor of 3, according to our first priority table, it's going to compress the function horizontally by a factor of a. So here, the x-intercepts or the t-intercepts at a function at 0.5. If we compress by a factor of 3, it's is going to be at 1/6 now. So over at 1/6, and the whole function kind of got squeezed and compressed in horizontally to produce this red function right here. Now, if we apply 0.2 sine h of 3t minus 0.5, what we're going to do is we're going to now compress it vertically. So now it's going to be down like this, into this lime green function right here, where it still has the same x-intercept, or t-intercept, I should say. And then if we take the same thing, 0.2 sine h of 3t minus 0.5, and then overall minus a 0.4, or minus 4, it's going to move down 4 units. And we finally get this black function, where we've applied all of our successive function transformations to get this. Hopefully this is all review for everyone. Does anyone have any questions? This is going to be very important when we're working with all these unit ramps and unit steps and such, is that we're very comfortable with function transformations so we don't get confused. Okay. Hearing no questions, we'll move on to the convolution definition. So we'll say f of t convolved with g of t is f convolved with g of t is the integral from tau equals minus infinity to infinity of f of tau times g of t minus tau d tau. So convolution f of t and g of t produces a new function in the same time variable t called f convolved with g of t. So one thing that's very important is you must use a 6-pointed star to represent convolution. That's just the convention. Now you have to be careful when you use your asterisk key. Your asterisk key doesn't always produce a 6-pointed star. You should look for a 6-pointed star. So Unicode, it's U plus 2217. HTML, it's and low AST. Semicolon, like there's all sorts of different ways to get this 6-pointed star that I'm using. And you should never ever confuse the convolution symbol with the multiplication symbol. So be very careful when you use the asterisk from now on in electrical engineering. So yeah, using the asterisk to represent multiplication is going to get really confusing in some situations. Now, must be a 5-pointed star, because, or 6-pointed star, because the 5-pointed star is cross correlation. An 8-pointed star represents something else. 6 is what we do. Sometimes they're written with the vertical bar and then 2 bars at 60 degrees. I handwrite it with a horizontal bar and 2 bars at 60 degrees, but like, I don't know. It's important that you use a 6-pointed star. Hopefully I've hammered that point home. Other than the sum being replaced with an integral over tau, and tau should disappear from the result, this mimics the discrete convolution formula. See that g of t is reflected within the d tau integrand, and that t represents the distance along the tau variable track. So multiply f of tau and the reverse and shift to g of tau across all of time. Result over after multiplication is integrated over all of the tau line to produce a single time instant of f convolved with g of t. And then before we shift g of tau infinitesimally further along. So unlike before, where we could literally just move g of or g of m, just one time instant along. Now we have infinitesimally, many an infinitesimal distance separating different time instants. So you can't really, do the tabular integration or anything like that to represent convolution. And guest person's back. So the trouble with convolution. So integrals are much harder to perform than summations. In general, you can't just multiply 2 functions and get something that you can integrate easily. Sometimes you don't even get something that can be integrated analytically. So, that's one trouble, is multiplication and integration. However, most functions we encounter have finite support, which is a fancy mathematical term That means that there are non-zero only over a finite interval. So remember that rectangular pulse where we subtracted two step functions? That means there's a finite support. That means there's only a finite interval where took on a non-zero value. Some other functions asymptotically approach zero, which is also handy because that means, we get an answer that should decay to zero as well. Or sometimes they're just otherwise nice functions like constants, sinusoids, so on and so forth. If convolving functions each with finite support, the convolution is just going to be the sum of the length of the two functions. So if f of g exists from 0 to 5 and g of t exists from 0 to 7, then that means the convolution is going to be of length 12, 5 plus 7. Some functions are going to use impulses, steps, and ramps, such that it's possible to convolve them graphically.
30 minutes.
Thank you. So we'll talk about graphical convolution next time. So the most important property about convolution is the sifting property right here. It's the one that we always should be happy to see and happy to use whenever we get a chance. So sifting property, think about straining something through a sieve, like in cooking, like you're trying to, get something to strain through a sieve. This is, the origin of the name sifting property. So x of t convolved with delta of t. Compressing horizontally and stretching vertically by the same factor don't produce the same resulting function. It'd be a really weird function. It wouldn't have any even or odd symmetry if it did. It'd be something like the diode function, where it's like an exponential -1 or something. And you treat that whole thing as like the parent function. So it'd have to be a function without even or odd symmetry. Aubrey. Anyway, the sifting function. So we'll convolve a function x of t with the sifting function, which, we'll get back x of t by definition. So convolving any well-behaved function to the delta function returns the original function. This means that the Dirac delta function is the identity element for the action of convolution, just like 0 is for addition, or 1 is for multiplication, or the function f of t is equal to t is when you compose two functions one after another. So we can use the sifting property evaluated at t equals t naught to extract the output of a function at a point. So if you were to just plug in, t naught into this function, you get x of t naught is equal to integral from -infinity to infinity x of tau delta of t minus t naught minus tau d tau. So here's a proof of the sifting property, something that you should hopefully get familiar with. So x of t convolved with delta of t, well, we'll just use our convolution definition. X of tau times delta of t minus tau d tau. And we note that the delta function is 0 everywhere except between where, right before and right after t, if we look at our limiting sequences. So since this is 0, multiplying something by 0 and integrating over, a definite interval, taking a definite interval of something that's 0 is going to give you a 0 result. So we only need to integrate from t equals, or tau equals negative t minus to tau equals t plus. But by the property of the delta function and the well-behavedness of x of t, that means x of tau is just x of t in that period. It's just a constant. In fact, it's a constant with respect to the tau integral we're integrating with. So we just factor the x of t out, and we get the integral from tau equals t minus to tau equals t plus of the delta function. But that's just an integral of 1 because the delta function has unit area. So we just get x of t. So this is the sort of quick proof of the sifting property. What questions we have? Hearing no questions, we'll move on to the time shifting property. So if we have x of t convolved with t minus capital T, we'll get x of t minus capital T. So this is the same proof as before by replacing t with t minus capital T where appropriate. So basically we put t minus capital T in here, then that changes all these things accordingly. So instead of having to apply the time shift to the original function, we can shift it through convolution with a shifted delta function. So basically, say, for example, we had some sort of apparatus that was really good at doing convolutions, but really bad at evaluating functions for some odd reason. Bear with me. This will, may not make a lot of sense, but just entertain the hypothetical that we have a function or an apparatus good at taking convolutions, bad at evaluating functions. So we can just feed this function in, it'll continuously spit out its convolution. So instead of having to time shift the entire function and feed that into our apparatus, we can just shift our delta function, and suddenly we end up with the shifted original function. So the convolution integral will perform the time shift for us. This is going to be useful when we discuss Laplace transforms, or sometimes rather than deal with time shifting the function, we'd rather just think of it as the convolution with a shifted delta function. So this is the time shifting property. You can time shift the original function by convolving with a shifted delta function. We'll get through one example. We have time. So here's a convolution example. So find y of t is equal to x of t convolved with h of t, given x of t is x sub a sine of omega t u of t, and h of t is equal to h sub a e to the btu of t. So by definition, it's just x of tau under the integrand times h of t minus tau under the integrand d tau. So first thing we could do is we know we have this unit step function here, which is 0 for all the time up until tau equals 0. So that basically means we can trim the limits of our integrand using the first step function. So u of tau disappears, and we just integrate from 0 up to positive infinity. Next, we can look at the second step function. And this function, because the tau is backwards, we can go back to our function transformation properties and say, okay, this function is 1 for all tau up to t, and then at time equals t, it jumps down to 0. So because it it's a backwards facing step function, we can trim the upper limit with the second step function. So the integral is going to be integral from 0 to t of sine of omega t tau e to the negative b tau, where we use the fact that these are constants to pull them outside of the integral. And when we broke up this exponential function into e to the bt times e to the negative b tau by exponent properties, e to the bt is a constant with respect to tau. So we can pull it out of the integrand. So now we have a sinusoid times an exponential. We can use integration by parts, IBP, on the integral. Or remember, integral from a to b of u dv is evaluation of uv between a and b minus integral from a to b of v du, where u is equal to sine of omega tau and dv is equal to e to the negative b tau d tau. Well, integral of sine of this is equal to this. We'll evaluate this and then use IBP again, this time using w is equal to cosine omega t and dz is equal to e to the negative b tau d tau. So when we plug in here, t is just t, tau equals 0. Remember, e to the negative 0 is just 1, but sine of 0 is just 0. So we'll get a 0 there. And then we'll get, this omega over b is a constant. And then we do integration by parts again. We get something that looks like this. We'll gather like integrals to get the evaluation equation. So this integral over here looks like our initial integral with some constants out front. So we can do some algebra and we get that, this is equal to -1 over b times quantity 1 plus omega over b quantity squared sine omega t plus omega over b cosine omega t minus omega over b e to the negative bt. But this isn't what we were after. We were after the convolution. So the convolution is up here where we need to introduce this xa, ha, and e to the bt again. So the e to the bt will cancel out that e to the minus bt where appropriate. And we get this. I'm starting to think I did this wrong. Yeah, that term shouldn't be there. Can't cross that term out. That's should just be a step. So there's no e to the bt left in the final answer. So overall, our answer of the convolution is negative x sub a h sub a over b, quantity 1 plus omega over b quantity squared, and then times sine of omega t plus omega over b cosine omega t minus omega over b closed quantity u of t. And that's our convolution. And yes, you will be expected to know how to do integration by parts on exam 2. So no getting out of that. That being said, I will take any questions now, and then I will head to office hours. I imagine some of you have questions about homework 2, where office hours will be useful. Office hours start at 11:30. Any questions? Hearing no questions, class is dismissed for today. Thank you for coming. And remember, if you have questions regarding the first exam, try to submit them to me by email so I can have something intelligent worked out for the next lecture. You're welcome, everyone. Have a good day. Bye.